So, today's khôlle was on matrix determinants on the 10th of April. So first of all, I was asked to give the definition of a matrix. So for all matrix A of size n by n with values in R or C, the determinant of A is given by the sum for permutations in the symmetric group of order n of the signature of the permutation times the product for I from 1 to n of the product of the coefficients of A in line I and column sigma I, or A of line sigma I and column I. So knowing this, in the case where n is equal to 3, so you have a 3 by 3 matrix, the symmetric group of order 3 is the identity, transposition 1, 2, 1, 3, and 2, 3, as well as permutations 1, 2, 3, and cycle 1, 3, 2. So, knowing this, that means that the determinant of A must be signature of identity. Identity is a function of 0 transpositions. 0 is even, so the signature is going to be positive. So we have A1, 1, A2, 2, A3, 3. Plus signature of 1, 2, 3. 1, 2, 3 is a permutation made up of 2 transpositions. 2 is even, so the signature of that permutation is going to be plus 1. So A1 goes to 2, A2 goes to 3, and A3 goes to 1. Same for this permutation, there's 2 transpositions in there, so it's positive, and product is A1 goes to 3, A2 goes to 1, and A3 goes to 2. Now for the negative signatures, each of these are 1 transposition. 1 is odd, so there's going to be a negative signature, so the product is going to be given by A1 to A2 to 1 and A3 to 3, negative. For this one it's going to be A1 to 3, A2 stays 2, and A3 goes to 1, and for this one it's going to be A1 stays 1, A2 goes to 3, and A3 goes to 2. So that's the determinant of a 3 by 3 matrix. Now there's a more visual method of finding this. If you write the matrix down as its coefficients, then you can find a determinant by rewriting the first 2 lines here underneath. So A1, 1, A2, 1, A1, 2, A2, 2, A1, 3, A2, 3, right? And then what you do is you go by diagonals. So if your diagonal is in this line, then you go positive, 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 and if it's in this side, you will go negative. So this will all be added negatively. And then you just follow the coefficients. So we're doing this side first, so positive. So that gives A1, 1 times A2, 2 times A3, 3, and what we can notice is that it's exactly what we have here. So we've done this diagonal. Next comes this one, A2, 1, A3, 2, A1, 3. Can notice that it's what we have here, so A2, 1, A3, 2, A1, 3. And then we can do the final one, so A3, 1, A1, 2, A1, 3, and you can notice 3, 1, 1, 2, 2, 3. Same idea for the negatives, except in going this way up. So we have this diagonal here, A3, 1, A2, 2, A1, 3. And you notice that this is what we have here, A3, 1, A2, 2, A1, 3. So negative A3, 1, A2, 2, A1, 3. Negative this diagonal here, A11, this one here, A11, A32, A23. And the final one where the 3 doesn't change, so A21 here, A21, A12, A33. Okay, so that's Sarrus's method for visually finding a determinant of a 3 by 3. So that's all pretty boring. Let's get to an example. This is a matrix here, depending on x, y, z, and t with values in k, so R or C. So first I was asked to find a determinant of M. So if you notice, this matrix is very similar to its transpose. The x's on the diagonal are the same and they're nowhere else. And there's a problem of sign between the coefficients and their transpose equivalent. So you might get the idea of multiplying M by its transpose, and when you do that you find that any coefficient that isn't on the diagonal is 0, and on the diagonal you always get x squared plus y squared plus z squared plus t squared. Yep, so that goes until 4 since it's a 4 by 4 matrix, and everywhere else you have 0. So knowing that, you will write down that determinant of M times the transpose of M is going to be equal to the determinant of x squared plus y squared plus z squared plus t squared times the identity matrix for 4 by 4s. Right, so you've taken this expression and you've passed it on to the determinant value. However, you know that determinant of A times B is determinant of A times determinant of B. And moreover, you know that the determinant of a transpose of a matrix is the determinant of that matrix. They're equal. So that means that the determinant of M all squared is determinant of x squared plus y squared plus z squared plus t squared times the identity of size 4. However, the determinant of identity of size 4 is going to be 1, and since you know that the determinant is multilinear, then you can take this expression out and raise it to the power of 4, because there are 4 times that expression on this matrix. So that gives you determinant squared of M is going to be x squared plus y squared plus z squared plus t squared to the 4. So then you pass the square root and you get determinant of M is going to be plus or minus x squared plus y squared plus z squared plus t squared. So then you have a problem on the sign. However, all squared. However, if you look here, you can treat it as a polynomial in x. When you look at it as a polynomial in x, then the only coefficient on x to the 4 is going to be dependent on this plus or minus sign. So knowing that and having that in mind, we look back to the matrix here, and you notice that the only way of getting a product of x to the power of 4 in this matrix is by multiplying these 4 x's together. So that means that the coefficient of x to the 4 must be positive, since the only way of getting x to the 4 from this matrix is multiplying all of those x's together, and there's no negative signs there. So we know that the sign of the determinant must necessarily be positive. So that's determinant of x. So to deduce m to the minus 1, what we can do is therefore use this identity here again, this here, that m times transpose of m is almost identity of size 4 with a factor close. By rearranging, we get m times 1 over x squared plus y squared plus z squared plus t squared. X squared there, times m transpose of m is I4. So that tells us that this here must be m to the minus 1. which also explains why this is similar to the determinant, since if it's 0 then m wouldn't be inversible, and this is coherent with what we have before. So next we're creating a set. M is the set of all matrices of this form for x, y, z, and t values in r or c to the 4. So now we need to show that M is a field. So we can write the set M as a vect of 4 matrices. So if we look at the matrix here that we have above, there are x's only on the diagonal, so M is the vector of the diagonal matrix, so the identity matrix for x. Now if we look at the y values, then we have one here, 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 and here, and there are only plus or minus 1s ordinating them. So we can write the y in the M as a matrix of 0, minus 1, 1, 0, 0, 0, 1, minus 1, 0. I'm missing a line. No, this is 0, this is 0, this is 1, this is minus 1, this is 0, 0, and 0. Right? So that's the y in there. Then we have the z. Z can only be found here, here, up here, and down here. So we can write that also in the vect. 0, 0, 1, 0, 1, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1, 0, 0. So that's the third vector that is in the smallest vector space from these vectors. And finally we have the vector that is holding t, so we have minus 1, 1, minus 1, 1 on the diagonal opposite from the other one. And 0 everywhere else. There, so that is already a good step forward towards showing that M is a field. That means that M is a vector space, is a k-vector space. So that already allows us to show that M is stable by the sum. So to show that M is stable by multiplication, then we could just take two big matrices with x, y, z, t, and x prime, y prime, z prime, and t prime, but that would take a lot of time. So what you do is what I did is I named this matrix J, this matrix K, this one L, and what I show is that J squared is minus identity of 4, which is the same for K squared and L squared, right? And then what I did is I showed that JK and KL can also be written as combinations of JK and L. So when you write your product of two matrices in this set M, so let's just say it's M and M prime, instead of writing M times M prime, you can just write it as X identity plus YJ plus ZK plus TL times X prime I4 plus YJ prime plus Z prime K plus T prime L. You can just write it as a multiplication by this, and then when you develop it out, you will already have a answer in terms of I, J, K, and L. So you can just deduce that it also stays stable by multiplication. So M is a set which is created as a vect. So it's a vector space. It's stable by addition, multiplication. The inverse is in the set only if the determinant is non-zero. However, the determinant is a sum of squares, So the only way of getting a determinant of 0 here is having x equals 0, y equals 0, z equals 0, and t equals 0. So that means the only non-invertible matrix in M is the completely empty matrix, so 0 everywhere. So that shows that M is a linear group. M times is a linear group, a multiplicative group, so what we've showed down here. So overall M is a field, and I've shown that M times is a multiplicative group as well. The only thing being left to show is that since M is included in the 4x4 matrices of values k, and I4 is in the set M, and we've shown that M is stable by multiplication, and that the inverse by multiplication of M stays in M4 of k. It stays in the set M, therefore M is a subgroup of M4 of k times, and is therefore a multiplicative group. So that was the matrices and determinants khôlle.